Welcome back, everybody. In today's videos, we're really just going to work through some of the problems that we started in class when we began modeling the greenhouse effect. The idea here is to start with a simple stock and flow model of energy in our atmosphere, and then to gradually increase the complexity until we have a fairly sophisticated and powerful climate model that we can use to inform all kinds of climate and energy policy. The nice thing is that the basic approach to creating and solving these stock models is basically the same to what we've seen before. The math isn't terribly difficult, but it is challenging to understand how the mathematical model relates to the physical systems and vice versa. So hopefully by going over these examples deliberately and slowly while increasing the complexity, we can gain a better understanding of how these systems work and how to interpret our results. We'll begin by looking at a problem that we did together in class, and we will model a simple climate system that contains just enough greenhouse gases to absorb all the outgoing radiation emitted by the surface of the Earth. To represent this model, we will use two stocks. First, we have a stock of energy contained at the surface of the Earth. Basically, sunlight is striking the Earth and causing it to warm, and that stored energy represents a stock. Similarly, we know that the atmosphere absorbs infrared energy that is emitted from the surface of the Earth, and as a result, the atmosphere warms and stores energy, and it represents a second stock. We represent these two stocks with two boxes, and we will label one of them E for the Earth, and we will label the second one A for the atmosphere. We also have flows of energy that are moving between these stocks. First of all, we have the sunlight that is coming in and striking the Earth. Remember that the greenhouse gases do not absorb visible light very well, so this flow is not interacting with the atmosphere, even though the light is passing through the atmosphere on its way to the Earth. The flow is a little bit complicated when we write it out mathematically because we have two terms. First, we have omega divided by 4, which is the total power density of energy coming from the sun. Here, omega takes a value of 1,372 watts per square meter, and it has units of watts per square meter because we are really looking at the amount of energy per unit area that is being absorbed at any given location on the Earth. Also, we have to divide by 4 because this energy isn't being spread out over a flat surface. If the Earth was shaped like a flat disk, and if we were only considering one side of that disk, every location on Earth would be receiving exactly 1,372 watts per square meter of power. However, the surface of the Earth is curved, and half the Earth is not receiving any sunlight at any given time. And when you average over the entire surface, each location is only receiving a quarter of the 1,372 watts per square meter of power. Next, we subtract omega over 4 because a certain amount of sunlight is reflected by clouds and other bright surfaces before it can enter the Earth stock. Remember that A is called the albedo. It represents how reflective the Earth is, and on average, it takes a value of about 0.3 or 30%. 30% of the light coming from the sun gets reflected. In addition to the sunlight coming in, we also have flows of energy between our energy stocks. As the Earth warms, it gives off its own light in the form of infrared radiation, and the amount of radiation depends on a physical constant called the Stefan-Boltzmann constant, which is equal to 5.67 times 10 to the minus 8 watts per square meter per degree Kelvin raised to the fourth power. It also depends on the temperature of the Earth raised to the fourth power, and this makes sense when you look at the units of the Stefan-Boltzmann constant. Similarly, the atmosphere warms and also emits its own infrared radiation. Unlike the Earth, the atmosphere has two surfaces, a top surface and a bottom surface, and it emits radiation both upwards and downwards. It emits sigma T to the fourth upwards and sigma T to the fourth downwards. The radiation going upwards escapes to outer space, and the radiation going downwards is absorbed by the Earth and leads to additional warming. This is what causes the greenhouse effect. Excellent. So we've drawn a beautiful box model that does a nice job of representing the greenhouse effect. Now let's see if we can use it to create a system of equations that we can use to solve for the temperatures of the atmosphere and the surface of the Earth. To do this, we write out our equations of steady state. We make the statement that, at least over the short term, the total amount of energy in these two stocks is remaining constant. This in turn means that the flows coming into these stocks must equal the flows leaving these stocks. And this allows us to create our mathematical relationships. If we start with the atmosphere stock, we can see that the only flow coming in is the flow of infrared radiation emitted by the surface of the Earth. This must be equal to the flows leaving the stock, which are given by the radiation leaving upwards and the radiation leaving downwards. And if we add these two flows together, we get 2 sigma TA to the 4th. Next, we can write out our steady state equation for the Earth stock. Here we have 2 flows coming in. We have the sunlight and we have the infrared radiation that is emitted downwards by our atmosphere. So we have omega over 4 minus A omega over 4 plus sigma TA to the 4th. The flows in equal the flows out, and we only have one flow out, which is sigma TE to the 4th. Now we have 2 equations, one equation for the atmosphere stock and one equation for the Earth stock. And this is perfect for us because we have 2 unknown temperatures that we're hoping to find. And in the next video, we will see how we can isolate these variables and solve for the temperatures of the Earth and the atmosphere.